Load types. The force or weight on a structure is its load. Structures are frequently subjected to combinations of different types of loads, which may be concentrated, distributed, or dynamic. All these forces can act together or alone on the structure. The duration of a load is also a contributing factor. A structure might be able to hold a large load, larger than its rated weight, for a short while, but because of the stress on the structure, it will fail quickly. Random forces that have no pattern and that do not repeat, such as lateral force during an earthquake, also have a negative effect on load-bearing structures. Loads can be of a particular type and have their own specific load effects. Dead load, the weight of the building materials alone. Live load, the additional weight due to occupancy or use, such as weights of people and traffic. Snow load, the weight of accumulated snow on a structure. Wind load, the force of wind pressure against the structure surfaces. Sometimes the dead weight of a structure does not significantly impact its load-carrying ability. For instance, the dead weight of bridge material is minimal compared with the applied load. However, the materials for structures such as earth dams and fill for highways weigh a lot more than their external loads. Concentrated load. A concentrated load acts on a relatively small area of a structure. If you place a 300 pounds load in the center of a small bridge, the weight is distributed over a given area, depending on the size of the base of the load. Even if the weight of the load is not evenly distributed along all edges of the load, the total contact area is still small compared to the total bridge surface. The total 300 pounds force represents a static, concentrated load of 300 pounds. Acting on the midpoint of the bridge. If you move that load toward either of the ends, the weight is still distributed, but it stresses the weighted end slightly more. The heavier the load, the more stress it puts on the weighted area. In addition, the structure of the bridge itself determines how much the load weight will affect the structure. If you place the same load on a beam structure, the stress will be significantly more than on a truss system. Figure 7.19 shows a concentrated load on a beam structure. 300 pounds. Figure 7.19 concentrated load. Static uniformly distributed load. Distributed loads extend their weight across an entire structural area, or along a line. A static uniformly distributed load applies a force on a structure that is uniformly distributed, that is permanent, and that does not vary with time. In this case, the load creates no specific stress point. For example, a large pipeline that crosses a gulch and is supported by a truss adds the weight of the fluid flowing in the pipe to the dead weight of the pipe itself and represents a uniformly distributed load carried by the truss. Other examples include a snow load on a roof, the lift on aircraft wings, and the vertical bearing forces on foundations. Figure 7.20 illustrates a static uniformly distributed load. Pipe. Dynamic and impact loads. If the applied loads vary with time, or the structure experiences a high degree of movement, then the load is dynamic. An example of a dynamic force is that of a motor, with an unbalanced rotating shaft mounted on a frame. As the shaft rotates, the magnitude and direction of the force will vary. Another type of dynamic load is an impact load. An air blast or shock wave is a sudden force with a large amplitude and relatively short duration time, as are car crashes and rocket thrusts. Non-uniformly distributed loads. In a uniformly distributed load, the weight or force of the load is distributed evenly across the entire surface of the structure. However, in some cases, the weight or force of the load is not distributed evenly. You can consider an evenly distributed load as a rectangular force, and a non-uniformly distributed load as a triangular force against the structure, as figure 7.21 shows. For example, the horizontal force of water against a dam increases linearly, horizontally, with depth. Mechanical and structural properties. Mechanical properties describe the response of materials subjected to applied forces. The properties defined in this section apply to all building materials, including metals, ceramics, organics, and polymers. Stress. The strength of a material is typically specified in terms of stress, which is the internal force per unit area within the material. When you apply a load at a right angle to a structure, that load can cause the members to bend and result in tension in the fibers on the outside of the bend. The stress distributes uniformly through the cross-section where the force is applied. The stress is tensile if the member is being stretched, and compressive if the member is being squished. You measure units of stress in pounds per square inch, psi, pounds per square foot, PSF, or newtons per square meter, N/m2. Forces that tend to twist, bend, shear, compress, or elongate a material can induce stress into a material. Strain. Some materials tend to deform, strain, when you place them under a load. This strain can compress the material or stretch it. Strain is measured by comparing the original length to the strained length. You must measure the change in length in the same units as the original length, so that you can develop a ratio for the two. A positive value indicates elongation, and a negative value indicates compression. Modulus of elasticity. The modulus of elasticity tells you how much a material or structure will deflect under a bending load, vibration, or resonant movement within a material, and how much stress it can take. Figure 7.21 Non-uniformly distributed load. Different materials deform differently under the same load, and some stretch more than others under equal tension. Up to a certain point, most materials act like an elastic spring. Because not all materials stress the same, you use three types of elasticity to define elastic stress. Stretch modulus, this is the longitudinal stretch, end to end. You remember the toy Stretch Armstrong? Yeah, it's like that. Shear modulus, the size of the material doesn't change, only the shape does. The stretch is horizontal, such as when you lay a heavy book on top of a stack of magazines. Because the magazine covers are generally slick, the individual magazines will shift horizontally in relation to the ones under and over them. Bulk modulus, a change in volume occurs because of pressure or compression, such as when you place a frozen turkey on top of a grocery bag that contains bread. It's the squish factor.
Don't forget to subscribe.